we begin our discussion of Chapter 9 then. Chapter 9 then is entitled officially The Chemistry of Some Water and Air Reactive Substances. What we're really talking about in this chapter, however, are flammable solids. Substances that are in the solid phase yet are capable of burning or combusting or all in some way producing some sort of hazardous substance when they react with air, water, or other kinds of substances. In the DOT system, these substances are in one of three divisions. There are the flammable solids. The flammable solids are, in this group, the least hazardous of these hazardous materials, although they still are hazardous and worthy of consideration. You can look at a flammable solid, they have the red and white stripes on the placard itself, in addition to that number 4 to indicate that it is in the solid phase as opposed to the liquid or the gas phase. Spontaneously combustibles have the half and half white and red. These are kind of the middle ground. These are substances that will burn in air on their own without any kind of outside interference. I don't need a match. I don't need a spark. I just need it to be kind of warm enough to do it. And then the last group here, dangerous when wet, these are given a blue placard. These are substances that will ignite when they come into contact with water. But to be in any of these groups, we have to follow the definition. The definition is that we have a substance that is in the solid phase, and it can undergo combustion with the presence of an ignition source under standard circumstances without changing any variables or adding an accelerant. So this is the minimum requirement. I've got a solid phase material. When I put it in the presence of heat or electrical shock or some kind of other ignition source of some kind, it's going to catch on fire. I don't need to change the atmosphere. I don't need to elevate it up to 200 degrees Celsius to get it to that point. These kinds of things are going to happen at normal temperatures, normal pressures. And I don't need an accelerant of any kind either. You know, something like a fuel accelerator kind of thing, that like the lighter fluid on a charcoal grill, something to help the reaction start and sustain over a period of time. As I mentioned before, these fall into 3 subclasses. The first subclass, that first placard, the striped placard, are the flammable solids. To classify in this category, the hazardous material has to fall into one of these 3 subcategories, one of these 3 criteria. First, it could be a desensitized explosive. That is a substance that, when it is dry, would actually be an explosive. But it has been desensitized in some kind of way, either by wetting it, putting it under water, putting it under alcohol, putting it inside some kind of substance that is going to limit its capability and its access to the air, and therefore suppress those explosive tendencies. It could be a self-reactive material. Self-reactive materials are thermally unstable. They encounter just the normal heat of their surroundings, and they undergo a strong exothermic kind of reaction. That strong exothermic reaction generates tons of heat. That bunch of heat gets used to create more decomposition. Or they could be combustible solids. Combustible solids, by definition, are materials that cause fire through friction or have a burning rate faster than 0.087 inches per second. So those are my class 4 sub 1. Those are my flammable solids. Again, it's got to be one of these 3 subclasses. It's got to either be a desensitized explosive, a self-reactive material, or a combustible solid. One of those 3 have to be true if it is going to fall into this class. Again, this is the lowest subclass, which means these are actually the ones that are the least hazardous. Now, as we are encountering these kinds of materials, there are some considerations that we have to look into. First of all, we have to remind ourselves that whenever anything burns, it is not the vapor, or excuse me, it is not the substance itself that is burning, but rather the vapor that is being produced from that substance as it melts or sublimes or evaporates. And it's no different for solids. So with flammable liquids, when we talked about class 3 materials in chapters 4 and 5, we looked at them from the standpoint of their vapor pressure, and more importantly, their flash point. The more vapor that was produced, the more dangerous we considered them to be. The more likely it was that they were going to have a flash point at or near room temperature. The less it evaporated, the more stable we said it was, the less of a hazard we were going to have with it. Well, the same is true for solids as well. Solids have the capability of sublimation. Sublimation is what occurs when a solid turns into a gas. Skips the liquid phase completely, goes straight from solid to gas. We see this most often, or at least most commonly, with things like dry ice, where dry ice goes directly from those solid pellets to a gaseous vapor. But it occurs in other kinds of situations as well. Ice, for example, normal water-based ice, snow, they go through sublimation processes as well, which is why when we have a big snow, like we did a couple of months ago, a lot of the times it does disappear kind of faster without, creating inches of water on the ground. Yes, the ground soaks up some of it, but sublimation actually is a big part of the reason why we don't have inches of water on the ground after big snow either. Some of the snow sublimes, some of it melts, some of it goes into the ground, some of it goes directly into the atmosphere. When solids vaporize, if they are flammable as vapors, we can detect their flash points just like we did for liquids. Now, in the case of carbon dioxide and water, neither of those vapors are flammable, so they don't have flash points. But for substances that are, we can measure their flash point and classify them based on their flash point as well. So, a couple of examples of these. Gum camphor and paradichlorobenzene. The paradichlorobenzene is what is found in mothballs. Mothballs give that very pungent odor that is associated with clothes storage. So if you have clothes that are stored in like an attic or in kind of a storage chest somewhere, mothballs are often stored with them to keep bugs from basically eating the fabric away. And they have an odor. The reason they have an odor, those mothballs will sublime, and the gaseous paradichlorobenzene puts off an odor in the air that basically tells the bugs to stay away. And they do. And actually people do too, because it smells pretty bad. But the downside with mothballs is that their flash point, a flash point of 150 degrees Fahrenheit, it's obviously not something that you're going to find in your attic on a normal day. But in the event of a fire, mothballs can actually help to accelerate that fire a little bit, since you got a big dose of heavy organic vapor ready to ignite right around a bunch of clothing. The second subclass, class 4.2, these are the spontaneously combustible solids. So again, we're talking about the middle ground here. Now, in this middle ground, we've got some pretty spectacularly nasty stuff. Pyrophoric materials. Pyrophoric materials are substances that will react, will ignite without any kind of ignition source whatsoever. So, by definition, a pyrophoric material is any solid or liquid, regardless of quantity, that will ignite within 5 minutes after coming in contact with air without any external ignition source. These particular substances are kind of nasty. If you are familiar at all with white phosphorus is stored underwater. And the main reason it is stored underwater is because it is pyrophoric, meaning that you will see it ignite in the air pretty much, not like almost instantaneously, but pretty darn close. As soon as it dries, it hits that air, it ignites. Well, it's illegal for most uses. For a period of time, white phosphorus was used as a chemical weapon. And they would rain white phosphorus down on enemy battle sites, and it would literally rain fire, because as that white phosphorus is coming down, it's igniting, and it would basically ignite anything that it came into contact with, which is why it was, as Josh said, it's illegal. Now, there is still some white phosphorus out there. Most of it is in laboratory kinds of situations, but it is nasty stuff. So that's what pyrophoric materials are. Now, inside of that group, we also have all of those metals that classify as Class D fires. So in here, you would find things like powdered aluminum, powdered magnesium, those kinds of things. Self-heating materials are substances that, when they are exposed to the air, they will go through a decomposition process. That decomposition process will generate heat. That generation of heat will cause the temperature of the substance to increase. As the temperature of the substance increases, it continues to decompose, it continues to heat, it continues to decompose, it continues to heat, and eventually it just ignites. And so again, this is something that happens without outside intervention. We don't need to do anything other than just expose this substance to the air, and it will start to react in this kind of way. The third subclass are the dangerous when wet. Now, the dangerous when wet, those are the ones that have the blue placards with the white letters on them. These are substances that will spontaneously ignite. They are flammable when they come into contact with water. That's their primary hazard. Now, also in this group are substances that may not necessarily ignite when they come into water, but they will react with the water in such a way and produce some kind of a toxic gas as a result of that reaction with the water. And so not all of these actually give us flammable materials. Not all of them actually give us fire, but they are generally reactive with water. And in that general reaction with water, we get something that we don't want. We either get a toxic gas or we get a material, a gas that is capable of igniting and causing a pretty nasty fire. These kinds of reactions where a substance comes into contact with water and makes some kind of a product, it's called a hydrolysis reaction. Hydrolysis reactions can come in a variety of forms. So, for example, potassium cyanide. Potassium cyanide qualifies as a material that will go in this particular subclass. The products of potassium cyanide with water are hydrocyanic acid when in water, or hydrogen cyanide gas when out of water. So hydrocyanic acid, if it stays in water, not too big of a deal. Chances are, though, it jumps out of the water, you end up having this toxic gas around. And anybody that knows anything knows that cyanide's not exactly good for your body. It is a rapid toxin. It's a neurotoxin as well. So oftentimes it'll start getting to your body before you really have a chance to do anything about it. The other product of this is potassium hydroxide. Potassium hydroxide we talked about in chapter 8. That is potash, a strong base, and a corrosive material. Depends on the quantity. It depends on the quantity. Most of the reactions that we have, so all of the alkali metals, all of the first group, they all react with water. And actually, I think we have I think there's part of a lab that you do where you'll actually put lithium and sodium into water and watch their reactions. Now we're only going to give you little bits of each one of them, but they react pretty violently even in those little bits. In larger quantities, yes, there are potentials for explosion. And we get into this here on this particular slide. When it comes to metals, most of the metals that we know don't really react with water at all. I take a piece of copper wire and I throw it into my bathtub. It doesn't do anything. I take my steel toaster and I run it under the hose. It doesn't do anything other than just destroy the toaster. But there are certain metals that are capable of reacting with water. And when they do so, they are quite violent when they do. And that violence, that reaction, that speed is increased when we get the metal into a form that increases its surface area. And so, of course, I'm talking about powders, shavings, turnings, any way that I can get that metal into a very fine form that is going to increase its reactivity, because it's going to increase the surface area, which means it's going to increase the reactivity of that substance to oxygen and increase the chances of reaction. But again, we are limited in which metals will actually react with water. I can shave copper down to the very finest of turnings. And if I put them into a bucket of water, they still won't do anything. I can do the same thing with steel, with iron. All that'll happen is that over time it will corrode, it will oxidize. But if I have anything in those first two groups of the periodic table, so we're talking about the lithium group and the beryllium group, those substances in those two columns of the periodic table do react pretty violently with water. And the further down the table we go, the more violent that reaction actually gets. So in the lab, we will give you lithium and sodium. And the lithium kind of fizzles around and dances on top of the water. The sodium will actually ball up, and you just see large amounts of hydrogen just kind of spinning that thing on top of the water. And as you go down, the reactions get more and more profound, more and more violent. Same thing in the alkaline earth metals. But to a lesser extent. The reactions with the alkaline earth metals aren't nearly as reactive, as prominent. The reactions themselves are as follows. Sodium will react with water to make sodium hydroxide and hydrogen gas and a whole bunch of heat. Calcium hydroxide will react with water to make, calcium will react with calcium, Calcium will act with water to make calcium hydroxide and hydrogen gas and a bunch of heat as well. So when it comes to looking at what's going on in these reactions and what we need to be on the lookout for, we're always going to find that metals react with water to give us hydrogen. That hydrogen is ultimately what is going to ignite to make fire. So whenever we see sparks or flames from these reactions, it is going to be from the hydrogen that is formed as a result of that. And if we get enough of it to happen, the heat of the reaction generally is enough to cause that to ignite. We also get from these hydroxides corrosives. Sodium hydroxide, calcium hydroxide, these are both corrosive materials. So you're kind of getting it from both ends here. The reaction can start a fire, and it leaves behind a solution that is highly corrosive. As I mentioned before, our reactivity with water does increase as you go down the group. So lithium is going to be less reactive than sodium, which is going to be less reactive than potassium, which is going to be less reactive than rubidium, and so on. Beryllium is going to be less reactive than magnesium, which is going to be less reactive than calcium. Group 1 overall is more reactive than group 2. It's for those reasons our alkali metals, the group 1s, we have to store them in mineral oil or kerosene, something to block their access to oxygen. Because if they get too much access to oxygen, they'll either oxidize and form like a thick coating, or they run the potential of potentially igniting where they sit. Group 2s aren't nearly as reactive, so we don't need to store them under kerosene or mineral oil. What we'll see instead is that most of them are reactive enough with the air that even when we have purified samples of these metals, they will usually have some kind of an oxide coating on them that needs to be stripped off or polished off before we use them. So calcium, for example, calcium is kind of a grayish black metal. kind of like steel, but you almost never see calcium that way. It always has this lightish gray to whitish appearance to it. And that lightish gray to whitish appearance is that calcium oxide coating that forms as calcium just naturally reacts with the oxygen in the air slowly to form calcium oxide. In the event of an alkali metal fire, where we are burning some kind of flammable group 1 material, obviously water is going to be ineffective against it because water will actually feed the fire, cause more hydrogen to be produced. Carbon dioxide really doesn't help much at all either because it doesn't provide a stable means to get rid of all of the heat that's generated, doesn't sufficiently block out the oxygen. So what we usually end up doing is we need a dry chemical agent of some sort. We've talked about graphite as being probably the most common Class D firefighter. And the reason for that is the graphite will react with the metal to form a carbide, and the graphite also acts as a good heat sink to pull away that excess energy. Because these alkali metal fires will often have corrosive materials associated with them, inhaling the vapors from them can usually be pretty nasty as well, because effectively you're breathing in strong bases. Lithium hydroxide, sodium hydroxide, potassium hydroxide in an aerosolized kind of form. And all those, once they hit the mucous membranes inside your respiratory system, would become bases and would cause some pretty considerable pain. Maybe not enough to really kill you or significantly harm you unless you really took in a lot of it, but it would definitely hurt. Well, if it's in your respiratory system, no. No, you would have to, they would have to give you some kind of a breathing treatment to try to work through that. If you ingested it, then probably they would probably give you a series of dealkalinizers, things that would gradually bring your pH up a little bit. But I mean, if it's going down into your body, it goes down into your stomach's full of acid. By the time it got to your stomach, you'd be okay, but you'd still have the damage in your esophagus from that base interaction. Now, in addition to those alkali and alkaline earth metals, there are other metals that are capable of catching on fire. Among them are magnesium, zirconium, titanium, aluminum, and zinc. Now, again, this is not something that we're going to see in bulk form. So if I have a big block of zirconium, it's not going to burn. If I have a big block of titanium, it's not going to burn. But if I get them in these very finely divided forms, powders, shavings, turnings, where the surface area is high and the heat is high too, that's when we can see these kinds of reactions taking place. The majority of stories I hear from people who have seen flash fires from grinding aluminum on their workbench. I've heard more than a few of those stories over the past 5 years since I've been teaching this class. It happens. It just does. The reason why, when you're grinding on that aluminum, you're creating these very fine shavings, and the friction of the grinder is generating a ton of heat. It doesn't take much for that to flash over and ignite. When it does, it is a Class D fire. Depending upon the extent of that fire, would give you an idea of what you need to do to put it out. Most of the cases that you guys would see, it's a flashover kind of event. It flashes, it ignites, and then it's over. Very rarely does it generate into much else, because once you see the flash occur, you generally stop what you're doing and deal with the fire issue. And since what you were doing was causing the shavings that were burning anyway, it usually kind of stops itself. Probably the most common of these is magnesium. Magnesium is a very reactive metal. It will react with water, although the reaction with water is incredibly slow. And I do mean incredibly slow. But we're more commonly known for looking at magnesium as an ignition tool, because when magnesium hits that ignition temperature, which is 1153 Fahrenheit, it will undergo a reaction to form magnesium oxide. And the reaction that does is very, very bright in its coloration. It's a bright, bright white light. Oh, really? Yeah, flints. Just to see what would happen. I was like, how long before you regretted it? Metallic magnesium is used in the fireworks industry. One of the reasons why fireworks kind of are bright when they explode. Most fireworks have small amounts of magnesium added to them for brightness. Magnesium is probably most prominent in the fireworks that are basically just the loud noise maker ones, the ones that give that real bright flash of white light and then a really loud sound. Those ones almost exclusively are magnesium based. But you will see that magnesium is often used for some of the other ones as well, just to help amplify the color so that you can see it against that dark sky. Metallic titanium. Titanium is used in a lot of applications because it has a lot of the same capabilities and strength as steel, but at a significantly lesser cost in terms of mass. So if you need lightweight strength, titanium is a common option if you can afford it. Another key advantage to it is titanium forms a titanium oxide coating because of its very slow reaction with the air. And that titanium oxide coating basically makes the resulting metal corrosion proof. So very difficult to oxidize it, very difficult to corrode it with acids and bases. Lots of strength, lots of advantages. Also a heftier price tag, which is why we haven't converted everything into titanium. However, in its powdered form or in its shavings form, it is pyrophoric. And as a pyrophoric metal, it will catch on fire and it has a potential for explosion because of how hot that reaction gets and how quickly it is able to produce those excess vapors. Zirconium. Zirconium is used in the nuclear and steel industries. It has an auto ignition temperature of 700 Fahrenheit, which makes it a little bit dangerous for use if the temperatures get too high. And again, with its finely divided forms, it is a fire and an explosion risk. The metal most of you are probably the most familiar with, other than magnesium, is aluminum. Now, aluminum, like some of our other products that we've talked about, aluminum does have a reactivity with air that is kind of slow, but its reactivity with air also produces an oxide. That oxide actually helps to protect the aluminum against other kinds of oxidation. However, aluminum is not protected by that coating from corrosion. So aluminum, as we saw in the previous chapter, is an amphoteric metal that is capable to both acidic attack and basic attack. So aluminum can react with strong acids. When it does, it forms hydrogen gas. That hydrogen gas is obviously flammable. We've talked on a number of occasions about what happens when you do those kinds of reactions. We've made reference several times to the works bomb, which is essentially what that is. Hydrochloric acid with a aluminum foil fuse, for lack of a better term. On the basic side, they are susceptible to base attacks as well. So aluminum is a very poor choice for building material. If that building is going to be in any kind of space where there is going to be significant exposure to acids or bases. The dust and the powder are pyrophoric materials. The dust itself is a participant in something known as the thermite reaction. Thermite reaction is actually a real process that is used in the steel production process. This is the thermite reaction. We'll actually close with it today. So the purpose of the thermite reaction is a lot of iron and rust in particular, comes to us in a oxide form. Now, in order to turn that oxide into iron metal that we could eventually use for steel, we've got to convert it into its pure form. The thermite reaction is one way to do that. Another common application of the thermite reaction is actually to create on the spot metal iron ingots that have been used for railroad repairs and other kinds of applications just in general. So we're going to set up the thermite reaction here in miniature. This is an example of, again, this is a real reaction. This isn't just a fun demonstration. This is a real reaction that is done by the railroad industry and others for creating hot metal in a flash, essentially, that can be molded and used for a number of purposes. So in the reaction here, they've combined aluminum powder and iron 3 oxide powder. They're going to use magnesium here as a fuse to help light and kickstart the reaction, because you need to have a little bit of an energy boost to get the reaction to occur the way that we need it to. So he's going to start by igniting the magnesium, and then we'll watch what happens from there. The magnesium's going down into the terracotta pot. The heat from that magnesium reaction is going to kickstart the reaction. Start to see some sparks here in a second. Now, the bottom of that pot is your molten iron that, like I said, could be dropped into the hole in a railroad track or used to create a rivet. Number of different applications for thermite. You can see it'll kind of drop through the bottom here, right about there. So if you do this reaction over the top of one of those holes, that molten iron goes straight into the missing spot. It acts as a patch. All right, so that's where we're going to stop for today. On Wednesday, we will finish up this chapter by talking about some other applications of flammable substances, and we'll take it from there. Have a good day.